Hello everyone, welcome to my channel, your physics mate. Today I am uploading a video after a long time. So the last video was about Boolean algebra, and today's video is going to be on the topic logic gates. I think you are wondering what is the basic relation between the logic gates and Boolean algebra. The basic applications of Boolean expression is based on logic gates. That is, if you want to realize the Boolean expressions practically, you need to have some logic circuits, and those circuits are nothing but the logic gates. And in today's video, we are going to discuss it thoroughly. And if you have any kind of queries about this topic or any other topic, you can write that in the comment section below so that I can make videos on them further. And if you like this video, please share it with your friends and please subscribe to my channel, and please feel free to ask any question about this topic, or if you want me to do any other video or on any other topic, you can also suggest those topics to me in the comment section. Okay, without a further delay, let's get started. Hello everyone, welcome to my channel, your physics mate. In the previous video, we have discussed about the Boolean algebra, and in today's video we will talk about the application of that one. That is, if we want to realize the basic Boolean algebra in practical purpose, we need to have some electronic circuits, and these circuits are called logic gates. The logic system and the logic gates is basically divided into three parts. The first one is called the basic building blocks. The second one is called the universal building blocks, and the third one is called the special logic gates. We all have heard about the basic logic gates, which are the AND, OR and NOT gate. These three gates are called the basic building blocks. Why it is so? Because they are the basic gates which are used in any electronic circuits. Okay, so they are called the basic building blocks. The next one, the universal building blocks. The Nand gate and the NOR gate is used to make the basic building blocks also, because these two gates, if we join them repeatedly one after another, they also can arrange a basic building block. That is, by using only NAND gates or only NOR gates, we also can have an AND or NOT gate, as the basic building blocks are made by these NAND or NOR gates just alone by them, so they are called the universal building blocks. And the third one, that is the spatial logic gates. These gates are basically used in communication electronics, okay, and in computer for the arithmetic logic circuit, for the arithmetic unit, these gates are also used there. They are called the spatial logic gates, and the basic examples of them is Zorgate and XNOR gate. Okay, so in this video today we will discuss about these three types of gates, and each of them are discussed here with their circuit symbols, with their truth tables, and many more. Okay, and at last of this video we will also discuss about some practical application of this all gates. So please don't skip the video and watch the video till the end, and if you have any queries about it, you can write it in the comment section below. Okay, so let's start. First of all, this is the one of the basic building blocks, which is OR gate. Okay, so the circuit symbol of OR gate, you can see it here. it is seen like this one. A and B are basically the inputs, okay, and OR gate have minimum 2 inputs, okay. You can have a 3 input OR gates also, but minimum you need to have at least 2 inputs for OR gate, okay. And y, if y is the output, then y is equal to A dot B. This dot is the OR operator. Sorry, this is not dot, this is A plus B, and this plus is the OR operator, okay. So the A and B are the basic inputs, and A plus B is the output. This is the basic OR gate, and if we write the truth table of this gate, this one is the circuit symbol, and the truth table is like that. If we have taken the inputs as 0 0 1 1 0 1 0 1, I already have mentioned this in the previous video why we have chosen in such way, so that no combination will be just overlooked, okay. So finally, if we write the output here, we have the output as y is equal to A plus B, right? So 0 plus 0 is 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 1. So only one situation, in only one situation, that is if the 2 inputs are 0, only then the output will be 0. Otherwise, if at least one input is on or at least one input is 1, then the output should be 1, okay. And if we write this lamp and switch arrangement, if we use a lamp and switch arrangement to realize the situation, how can we realize it? Well, we can do this one. This one is a key, this one is also a key, and we are putting the 2 keys parallel to each other, and we are using a lamp here, okay. This one is a lamp, okay. So this is A input, this is B input, and the Y output is the lamp, okay. So if A is on, that is this key is closed, and B is 0, that is B is open, then also the current will flow inside the circuit, and we are going to give a battery here, okay. So this is a battery. So the current will flow through the circuit and the bulb will switch on. The next one, if we have the B is closed, that is B is 1 but A is 0, in that scenario also current will flow through this line and the bulb will be on. And if the 2 of them are 1, that is A is on, B is also 1, then Y will also be 1 because the current will flow through both of them. And the final scenario, if both are open, that is 2 are 0, those 2 circuits, if 2 of them are 0, in that scenario only, okay, in that scenario only the current will not flow through the circuit because both of them are open. So in this scenario, that is 2 of them are 0, in that case only Y will not be enlightened. Otherwise, if A is on or B is on or both of them is on, then the Y, that is the output, will shine, that is Y will be on. Okay, the next one is the AND gate. Okay, so AND gate, here we are taking 2 inputs as A and B, and the output Y is given as Y is equal to A dot B, okay. So this dot is the AND operator, and this one is the circuit symbol of AND gate, and the truth table is such that Y is equal to A dot B, that is 0 dot 0, we have 0, 0 dot 1 we have 0, 0 dot 1 dot 0 we have 0, 1 dot 1 we have 1. That is, if we are going to have a AND operator, is operated in the logic circuit which is called a AND gate, okay. So the input, if we are taking input in this manner, that is 0 0, it will be 0, 0 1, it will be 0, 1 0, it will be 0, and 1 1, it will be 1. That is, if two of the inputs is on, only at that scenario the output is on, otherwise it will be off. Okay, so in this scenario, how can we have it with a lamp and switch arrangement? In this case, we are going to have the keys in series, okay, and this is the lamp. The lamp is not so good looking anyways. So in this scenario, you can see if A is on, this is A and this is B. If A is on, that is this one is closed, and B is off, that is it is open. In that scenario, it is open, so the circuit is open and the bulb will not glow. That is 0. Okay, if A is 0 but B is 1, that is B will be closed but A is open, that is A0 B1, that is this scenario. Okay, in that scenario also, this circuit is open and current will not flow through the circuit and the bulb will not glow. Okay, and if both of them are open, that is A is 0 and B is 0, in that scenario also current will not flow through the circuit and the bulb will not glow. That is the first one. So we have already discussed about the 3 scenarios, and finally the last one, that is both of them are 1, that is A is closed and B is closed. In that scenario, current will of course flow through the circuit and the bulb will glow. Okay, the bulb will glow, and this is the last one. So this is how we can arrange a lamp and switch arrangement, by which we can design this kind of circuit practically. Okay, and the final one is the NOT gate. This is the basic building blocks, the last basic building block. Well, NOT gate is basically a gate by which we are just complementing the one. That is, if we are giving A, we will get A bar in the output. That is, if we are going to give 1, the output will be 0, and if we are going to give 0 in the input, the output will be 1. That is, the output is the complement of the input, right? So this is the basic symbol or the circuit symbol of NOT gate, and the input and output is such that if we are giving a 0, the output will be 1. If we are going to give a input 1, the output will be 0. Okay, so this is the basic 3 basic building blocks, AND, OR and NOT gate. And the next one is the logic gates, which are basically the universal building blocks. That is, we are now going to discuss about these cases, universal building blocks. Okay, so there are 2 types of universal building blocks, that is NOR gate and NAND gate. And why they are called so? Because by repeated arrangement of them, we can have the basic building blocks altogether. So NAND gate, the circuit symbol of NAND gate is shown in the figure. That is, A and B are the inputs. Okay, NAND. This NAND has 2 parts. One is the in for NOT, and the other part is AND. So of course you can understand from this scenario that if we are going to give a NOT gate with this AND gate, NOT plus AND is going to make an AND. So here we have a AND gate, that is this D. This D is the AND gate. We have the circuit symbol of AND gate this way, and with that we are going to give a bubble. This bubble is for the NOT gate. Okay, this is the NOT gate, and this NOT gate is used here as bubble, so that what will be the output? The output is A dot B is the output of AND gate, and with that we are giving an additional NOT gate here. So we are giving a bar of this as an additional NOT gate is used here, and from this we have this by using De Morgan's principle. So A bar plus B bar. So let us see what happens here. So if we are giving both of them are 0, that is 0 dot 0 will be 0 and that bar of 0 will be 1. Okay, the next scenario 0 dot 1 will be 0, that bar will be 1. The third one 1 dot 0 will be 0 and that bar will be 1, and final one 1 dot 1 will be 1 and that bar will be 0. So we can have that only in the case when both of them are on, only in that scenario the circuit will switch off, which is basically absolutely reversible or absolutely the reciprocal of that one which is in the AND gate. Okay, we will see here the truth table of AND gate. You can see in every scenario it is 0 only if two inputs are on, that in that scenario only the output will be 1. But in the NAND gate, each of the input for each of the combination the output will be 1, and for only one scenario, that if the two inputs are on, only that scenario the output will be off. Okay, so this is basically absolutely reverse of that one of AND gate. So NAND gate is absolutely the reverse of AND gate. So it is a NOT plus AND gate. In the similar way, for NOR gate we have a NOT plus OR gate. So this is the basic circuit symbol of NOT gate, OR gate, and this bubble is representing the NOT gate. Okay, so of course for OR gate we have the output is A plus B, and if we are going to give a bar of them, that will be a NOT gate. Okay, so by using De Morgan's principle we are going to have A bar dot B bar. So for the input and the output, this truth table will look like something like 0 plus 0 will be 0 and that bar will be 1. 0 plus 1 will be 1 and that bar will be 0. 1 plus 0 will be 1 and that bar will be 0. 1 plus 1 will be 1 and that bar will be 0. So in this scenario, only in the case when the both of the inputs are 0, only then the output is 1, otherwise the output will be 0. Just see, it is the reverse of the OR gate. So let's see the truth table of OR gate. We'll see. Here only if the both inputs are 0, only then the output is 0, otherwise it will be 1. But here only if the both inputs are 1, it will be 0, otherwise it will be 1. That is, this is basically the, here only for the NOR gate, if both the inputs are 0, then output will be 1, and in other scenarios, for any other combinations, the output will be 0. That is the basically reverse of OR gate. So, OR, if we are doing a reverse OR gate or a NOT plus OR gate, it is called a NOR gate. And by using this NOR gate and NAND gate repeatedly, arranging them, we can have the basic building blocks. That is, the AND, OR and NOT gate can be made by using NAND only circuit or NOR only circuit. So they are called the universal building blocks. Okay, and how they can be doing this, we will discuss it in any other video. Okay, so we are not going to discuss it today's video because otherwise it will be much more longer video. Okay, so finally the last one, that is the special building blocks or the special gates. Okay, the special logic gates, and these special logic gates are used in the communication electronics, and basically they are used in the arithmetic section of a computer. Okay, so this XOR and XNOR gate, we are going to discuss it now. Well, now the Zorgate and XNOR gate. Okay, these gates are specially used in digital design, and so that they are also available in the IC form. Okay, so IC is the integrated circuit, and so this kind of gates are specially used in the arithmetic section of computer, and they are also used in the electronics and communication purpose. So they are called the special logic gates. Okay, so they are used basically used in heavy works. So they are used also in IC formats. Okay, well, the XOR gates, the special logic gates, first one is the Zorgate, and the circuit symbol you can see it here. This is the circuit symbol. Somehow it is looks like OR gate, but as it is a special OR gate, that exclusive OR gates or XOR gate. XOR is also called the exclusive OR gate. Okay, exclusive OR gate. So they are called the XOR gate. Okay, so also called the XOR gate, XOR gate or exclusive OR gate or XOR gate. Okay, so this circuit symbol is quite looks like the OR gate, but here something also adds on in this figure, that is this portion is looking like the XOR gate, but here some carved line is also used here. So this one is the circuit symbol for XOR gate. A and B are the inputs, Y is the output. This plus and round over plus is called the XOR. For this one is the Boolean expression of XOR, and this is basically the symbol of XOR function. Okay, so how the XOR operator operates? If there is within some two variables C and D, if you have a plus and a round over this one, this kind of symbol over there, then this is called the XOR operator, and this means it is C D bar plus C bar D. Okay, so this is the basic of XOR operation. Now this is the Boolean expression for XOR gate, and this is the circuit symbol of XOR gate, and this one is the XOR operator. So the truth table of XOR gate is looks like this, and for this every combination what will be the output? Let us see it here. If we have both of the inputs are 0, from here what will you have? Both of the inputs are 0 and you will have a 0 there. If both of the inputs are 1, the last scenario, if both of the inputs are 1, in that scenario also you will have a 0 over there. If one of the input is 0 and the other one is 1, that is 0 and 1, A is 0, B is 1, what will be happening here? A is 0, B is 1. In that scenario this will be 0, but this will be 1, so it will be 1. Okay, 1 and 0, if A is 1, B is 0, then A is 1, B is 0, it will be 1. But it will be 0. Anyways, 1 plus 0 will be 1. So from the truth table you can see that the output is 1 when the inputs are unequal. That is, one of them is 0 and the other one is 1. Right? And if both of the inputs are equal, that is both of them are 0 or both of them are 1, then the output will be 0. Only the output will be 1 if both the inputs are not equal, that is they are unequal. So these circuits or this kind of gates or these XOR gates are called inequality detectors, because if the inputs are unequal, only in that scenario the output will be 1. So these XOR gates are also called inequality detector. Okay, so this one is a very important question, why these XOR gates are called inequality detector, or sometimes it is also called that which gates are called inequality detectors and why. So okay, this is the answer of that question. Okay, the next one and the last one is XNOR gate. Okay, from the XOR gate you already have known that this is called exclusive OR gates. So these are called exclusive NOR gates or also XNOR gate. Okay. So if we add a NOT gate with XOR gate, that is, if we are adding a NOT plus XOR, it will become an XNOR gate. Okay, so you can compare the circuit symbols. Here we have no bubble here, right? You have a curved line and then an OR gate. This is called XOR. And if you have a curved line and a OR gate and plus a bubble, that is a NOT gate with them, in that scenario it will become a XNOR gate. So the expression or the Boolean expression of XNOR gate is something like this: AB plus A bar B bar, if A and B are the inputs here. Okay, you can look like this. If we take A XOR B and we give it a bar of them, what will happen? You will have an A B bar plus A bar B. From the previous calculation, we already have had it before. That is, if we have A XOR B, that means A B bar plus A bar B, right? So we are giving here A XOR B and bar of that. So A XOR B means A B bar plus A bar B, and bar of that means the bar of the whole thing. That means from De Morgan's principle, A B bar dot A bar B bar, right? Okay, it means from this portion we get A bar plus B bar dot, from this portion we get A bar plus B bar, right? So A bar plus B, because B bar means B. Similar way, from here we get A plus B bar, because A bar means A. Okay, so just from this product A bar plus B dot A plus B bar, we are just going to product this two. That is, A bar dot A means something into that one's bar gives us 0. Okay, the next one is AB. So AB plus A bar B bar, A bar B bar, and the third one is B bar. B bar into B gives a 0. So we are getting AB plus A bar B bar. We have just started from it A XOR B bar, and it becomes AB plus A bar B bar, which is the expression or the Boolean expression of XNOR gate, right? So the XNOR gate is basically nothing but the reciprocal or the reverse or the complement of XOR gate, right? So this is XOR gate plus NOT gate, that is the complement of XOR gate, is called the XNOR gate. So from the truth table, if we do this, we are using this Boolean expression to find the truth table, that both of them are 0, we will get a 1. If both of them are 1, we will get a 1. If any one of them is 0 and the other one is 1, from here, if A is 0, B is 1, it will be 0, it will be 0. From if A is 1, B is 0, it will be 0, it will be 0. So it is a 0. So from here you can find that if both the inputs are equal, only in that scenario the output will be 1. Otherwise, if the two inputs are unequal, the output will be 0. So if the both inputs are equal, the output will be 1. So that this kind of gates are called the equality detector. In the previous case it was an inequality detector, and in this scenario the XNOR gates are called equality detector. So it is a very important question, which gates are called equality detector and why. Okay, so I think you got understand it from today's video. And one thing more, we can write it here. You can also use this Boolean expression to define a logic circuit. Okay, so for this one is the XOR gate. So we are going to have y equal to a b bar plus a bar b, and you can use a logic circuit to define this Boolean expression. Okay, so we are taking A input and B input. Okay, so how can we manage it? First of all, take this one A B bar. Okay, so take a line from A and take a line from B and put a NOT gate here. So it will be a B bar and this will be A. A into B bar means we are going to have a AND gate here. So this portion, the output over here will be A B bar, right? The next one, this portion is A bar B. That is, we are going to have A. So we are taking a line from A, and when we are crossing the line of B, we are just bending the wire a little bit, and this one is A, right? So we are giving A and we are taking a B here. So B we are taking as it is. Okay, and both of them are in product. So we are just putting the inputs in a AND gate, and the output will give us A B. So this one is AB, but we are going to have A bar B, right? So we need to have a NOT gate over here. A, this will give a bar, right? So this will be A bar B. So it will be A bar B. And then finally, there is a plus sign in between. So we are going to have an OR gate over there. And the final output will be y is equal to A B bar plus A bar B. So in this way, this is the basic circuit realization of this Boolean expression. Similar way, you also can have a circuit realization of this one, this Boolean expression, that is A B plus A bar B bar, which is your home task. Try it by yourself at home, and if you have any problem, please write it in the comment section below so that I can resolve it. Okay, so I think you have found today's video helpful, and this video has already been a little longer, so we are not discussing any kind of applications today in this video, but of course I will definitely upload one more video with some applications and with some problems and their solution about this logic gates. Okay, so okay, it's all about today's video. I think you have found this video helpful, and if you find so, please like this video, share this video with your friends, and please subscribe to my channel. Thank you.